Welcome to this video. We're going to be talking about inverse functions. This aligns to IXL Precalculus A15 and A16. So suppose it was 77 degrees Fahrenheit outside and you wanted to know what the temperature was in degrees Celsius. You look online and you find the formula below. C of F equals 5 divided by 9 times F minus 32. So you plug in 77 to your function and calculate that 77 degrees Fahrenheit is equal to 25 degrees Celsius. But then your friend asks you to figure out what is 30 degrees Celsius in Fahrenheit. How do you go backwards? Is there another formula for f of c? The functions f of c and c of f would actually be considered inverse function because the input and output values are switched. So let's derive the function equation of f of c from the one we looked up online, c of f. So here's my original equation with c of f. I'm going to actually replace c of f with y and f with x for the sake of simplification. Now to find inverse, I'm going to actually swap x and y. So this becomes x equals 5 over 9 times y minus 32. And I'm actually going to solve this equation to get y by itself. So first I'm going to get rid of the 5 over 9 by multiplying both sides by 9 over 5, which is the opposite. So that cancels and I get 9 over 5x. This and this will cancel, equals y minus 32. Then I'm going to add 32, and I get 9 over 5x plus 32 equals y. And if I rewrite it with the right variables, it's going to be f of c equals 9 over 5c plus 32. So this and this are inverse functions. Now if we graph the original function c of f equals 5 over 9 f minus 32, we get the graph below. Can we use the graph to find 77 degrees in Celsius? What about 30 degrees Celsius in Fahrenheit? We can. So if we go over to 77, because the x-axis is Fahrenheit and the y-axis is Celsius, go over to 77, this would be 72, 74, 76, 77, and we trace up and find our point of intersection and then trace over, we see that's right over here at 25 degrees Celsius. And we can do the same thing backwards. If we start at 30 degrees Celsius on the y and then trace over, we said it crosses right here, and then we trace down, and we see that that's right here at 82, 84, 86 degrees Fahrenheit. Now, some functions don't have inverse functions at all. Think about f of x equals x squared. We can input any real number for x, but our output is always going to be a positive number because anything squared is positive. So does negative 2 equals x squared have a solution? It doesn't. So a quick way to determine is using something called the horizontal line test. If a function is graphed like this and we draw a horizontal line and it crosses more than once, we know that graph is not invertible. Now invertible just means has an inverse, so this does not have an inverse. Now the second one though, we draw a horizontal line, it only intersects once, so we know that this is invertible. In other words, it has an inverse. Although a function may not have an inverse on its entire domain, it might have one on just a portion of the domain. For example, if we go back to the function f of x equals x squared, and we restrict it to only be positive numbers, so the set of x such that x is greater than 0, then it actually becomes invertible. Look at the graph below. Usually you would have this continue on the other side, and then it would fail the horizontal line test. But in this case, we don't have that. We only have the left-hand side, the right-hand side, and it does pass the horizontal line test. So by restricting the domain, we made this function actually invertible. Let's practice. For each of these, we're going to find the inverse of the function given and then restrict the domain if necessary. So on this first one, there's not going to be any need to restrict the domain because this is just a line. It looks just like this. So no need to restrict the domain on this function. Let's just find the inverse. So I'm going to rewrite it with y instead of f of x. Then I'm going to swap x and y and solve for y. So first thing, I'm going to minus 2. I get x minus 2 equals negative 4y. And then I'm going to divide by negative 4. And my final result, if I write it the other way around, is y equals x minus 2 divided by -4. Okay, let's try this next one. Now this one is actually going to need a restriction on the domain because x cannot be, under here cannot be a negative number, which means x has to be greater than -2 or equal to. So that's my restriction on the domain. Let's go ahead and find the inverse now. So y is going to equal 9 times the square root of x plus 2. Let's swap x and y. So this becomes x equals 9 times y plus 2. First thing, I want to actually divide that 9 on both sides. So it becomes x divided by 9 equals square root of y plus 2. Now to undo a square root, I'm going to actually square both sides because that's the opposite. Then I get x over 9 squared equals y plus 2 because it undoes the radical. Lastly, I'm just going to subtract by 2, and I get my inverse function as x over 9 squared minus 2. Now let's practice using the graph of the function to find inverse values. So first let's actually just find a value of the function f of -1. So we go over here to -1, and then we go down, we see that hits right here at -2. So f of -1 is going to be -2. Now we use this little notation with the -1 in the top. That means the inverse. So we want to find the inverse of -8. So in other words, what value, if we trace over, hits at -8? Well, -8 hits right at -2. So actually this one also equals -2. Lastly, let's practice using the horizontal line test to determine if a function is invertible. On this first one, obviously, it only crosses once, so this one is indeed invertible. The second one crosses twice, so this is not invertible unless you were to restrict the domain. Alright, that's it for this video. Now go and try some practice on your own.